Today, we're diving into this really fascinating puzzle that Isaac Newton himself actually stumbled upon. And it all starts with something super simple, a thrown apple. But it ends with this profound mathematical truth that was kind of hiding in plain sight the whole time.
So here it is. This is the central mystery we are going to unravel today. When Newton was calculating the flight of an apple, his own equation gave him an answer he totally did not expect. At first, it seemed like it defied all logic, but what it really did was reveal a much, much deeper story.
Okay, so to get to the bottom of this, we've got to start right where Newton did, with his famous equations of motion. I mean, these were the revolutionary tools he built to describe and predict how pretty much everything moves, from apples all the way up to planets. Now, what's really interesting here is that Newton noticed something peculiar about one of his key equations. See, the variable for time wasn't just t, it was t squared. And that little detail meant he was dealing with what's called a second-degree polynomial. That tiny squared symbol sparked his curiosity. What did that actually mean for the physics of it all?
So to find out, Newton did what great scientists do. He decided to test it. He came up with this simple, really controlled thought experiment. You've got an apple, and it's launched straight up at a very precise speed, 20 meters per second. The goal? Super simple. Just measure the time it takes to hit a specific target height.
And this is where things get a little strange. This very simple experiment led to a result that just didn't seem to add up at first, creating this little puzzle that was just begging to be solved. Okay, so Newton picks a specific point in the apple's journey to focus on. All he wants to know is, when exactly will the apple reach this target height?
And he chooses 15 meters. A nice, straightforward target, well within the apple's reach. He sets up his clock, and he waits.
And here it is. This is the conflict. In the real world, he sees the apple hitting 15 meters at exactly 1 second. Perfect. But when he plugs 15 meters into his polynomial equation, it doesn't just give him 1 second. It spits out a second answer, 3 seconds. What?
You can almost hear him asking himself this exact question. The real world gave him 1 answer, but the pure mathematics gave him 2. This wasn't a mistake. His math was solid. So what was this ghost value of 3 seconds trying to tell him?
And then, that aha moment, the first big breakthrough. He realizes the equation wasn't just tracking a one-way trip. Of course, the apple passes 15 meters on its way up at 1 second, but then it keeps going, hits its peak, turns around, and passes 15 meters again on its way back down at 3 seconds. The math knew the whole story all along.
I mean, that's a brilliant insight, but a good scientist has to be sure. To confirm his theory was right, Newton decided to push the equation to its absolute limits. He's going to test its predictions at the very extremes of the apple's flight.
So let's look at what he found. When he set the height to the apple's absolute peak, 20 meters, the equation gave back only one value for time, which makes perfect sense, right? The apple is only at its peak for just a single instant. Then, when he plugged in a height it could never possibly reach, like 25 meters, the equation gave no real answers at all. It was behaving perfectly.
So Newton's conclusion was crystal clear. His equation wasn't flawed at all. In fact, it was incredibly powerful. It wasn't just calculating a single moment in time. No, it was describing the entire symmetrical journey of the apple. And this led him to the final, really beautiful solution.
And this is where all the puzzle pieces just click right into place. The solution isn't just a number, it's a shape. It's this elegant curve that visually connects the physics to the math.
This right here is the key to the whole thing. Every single second-degree polynomial, just like the one in Newton's equation, can be drawn as a graph. And that graph always produces the same distinct shape, a parabola.
And this picture just brilliantly illustrates the entire mystery. If you plot the apple's height over time, you get this perfect parabolic curve. The y-axis is height, the x-axis is time. Now look, if you draw a horizontal line at 15 meters, it crosses the curve in 2 places, at 1 second and at 3 seconds. Draw a line at the peak, 20 meters, and it just touches the curve once. And a line above 20 meters, it doesn't touch it at all. The graph is a perfect picture of the apple's entire flight.
So the ultimate takeaway here is incredible. Newton's equation wasn't just some simple calculator for one moment in an apple's journey. It was this powerful engine that was describing the complete, elegant parabolic path it took through spacetime. A simple formula held this beautiful hidden geometry.
It really makes you wonder, doesn't it? If a parabola can so perfectly describe a simple thrown apple, what other fundamental truths about our universe are just waiting out there to be discovered, hidden inside the elegant curves of pure mathematics?